Have you ever wondered how your computer manages to run multiple programs at once? The answer lies in the heart of your machine's operating system, with an entity known as a process. A process is essentially an executing instance of a program, complete with its own resources and execution context. Think of it as a self-contained unit of work that's running your program. It has its own address space, resources, and context. It's like the conductor of an orchestra, managing and directing each note to ensure the symphony plays without a hitch. Each process includes the program code, data, stack, heap, and other information vital for execution. They are created by the operating system when a program is executed, with the operating system allocating necessary resources and initializing data structures to represent the process. That's the magic of processes, the fundamental units of execution in operating systems. So, how does a process come into being? This is where the magic begins. When a program is executed, the operating system steps in to create a process. It's kind of like a production line. The operating system allocates necessary resources, such as memory and CPU time, and initializes data structures to represent the process. It's a meticulous process, with the operating system ensuring that each process has what it needs to run smoothly. Now, each process is a unique entity. It's like a snowflake, no two are the same. This uniqueness is maintained through a set of attributes. One of the key attributes is the process ID, or PID for short. This is a unique identifier assigned to each process by the operating system. Think of it as a name tag, ensuring that each process is easily identifiable. The state of a process is another important attribute. It's like a status update, indicating the current stage of execution. Processes can be in various states such as running, ready, blocked, or terminated. Just like us, they have their busy days and their idle moments. Some operating systems also assign priorities to processes. This is crucial in determining their scheduling order. It's like a pecking order, determining who gets to go first. Each process, except for the initial one, has a parent process that created it. It's a familial connection, tracing the lineage of each process. The resources associated with a process are another key attribute. These include CPU time, memory, files, and I/O devices. It's like a process's personal toolbox, containing everything it needs to get the job done. So from creation to acquiring attributes, a process is carefully crafted and identified by the operating system. It's a fascinating journey, with each process playing a vital role in the functioning of our computing systems. As we move forward, we'll delve deeper into the life cycle of a process, exploring how they execute, communicate, and eventually terminate. But for now, let's take a moment to appreciate the intricate dance of creation and resource allocation that brings each process into existence. Now let's delve into how a process executes and how the operating system manages this execution. Process execution is a fascinating dance, choreographed by the operating system. This dance can take three different forms: sequential, concurrent, or parallel execution. Sequential execution is like a solo performance, with one process executing at a time. Concurrent execution, on the other hand, is like a synchronized group performance, with multiple processes appearing to execute simultaneously. This is achieved by rapidly switching between processes, a technique known as time sharing. Lastly, parallel execution is a grand ensemble, with multiple processes genuinely executing simultaneously on multiple processors. The operating system's choreography, or scheduling of processes, is crucial for an efficient performance. The scheduling algorithm, much like a dance director, decides which process takes the stage next. It pulls processes from the ready queue and allocates them CPU time. This process is called dispatching. But what guides the decisions of this dance director? The scheduling algorithm aims to optimize system performance based on a few key principles. First, it strives to maximize throughput, which is the number of processes that complete their execution per time unit. It's like trying to ensure as many dancers as possible get their moment in the spotlight. Second, the algorithm aims to minimize response time, the time it takes from when a process is submitted until it starts to respond. It's like making sure a dancer doesn't wait too long in the wings before their performance. Finally, the algorithm ensures fairness among processes. It's like ensuring all dancers, regardless of their roles, get equal opportunity to perform. Some operating systems even assign priorities to processes, with high-priority processes getting more time on the CPU stage. Thus, the operating system efficiently manages the execution of processes, ensuring optimum system performance. Just like a well-directed dance performance, the result is a system that's responsive, efficient, and fair. Ever wonder what happens when the operating system switches from one process to another? Well, it's like a magic trick that happens right under your nose, and it's called context switching. Imagine you're reading a book and you suddenly have to stop to take a phone call. You'd probably mark your page, right? That's essentially what the operating system does with the currently running process. It saves the state of that process, which includes details like the program counter, registers, and variables. This stored state is like a bookmark for the process, allowing the operating system to know exactly where it left off. But the magic trick isn't over yet. The operating system then pulls out another bookmark, this time for the next process that's ready to run. The state of this new process is restored, which is like opening the book to the marked page. With everything set up, the next process can now take the stage. Now you might be wondering, how do these processes interact with each other? Well, they have their own way of chatting, called inter-process communication, or IPC for short. IPC is like the postal system for processes. It allows them to exchange data, like sending letters back and forth, but it's not just about sending and receiving. IPC also allows processes to synchronize their operations, like coordinating a team effort. Imagine a group of musicians in an orchestra, each playing their part, but also listening to others to stay in harmony. That's how processes coordinate their activities using IPC. So in the grand performance of an operating system, context switching is the stage manager, ensuring each process gets its turn in the spotlight. Meanwhile, inter-process communication is the conductor, guiding the processes in their coordinated efforts. Together they create a symphony of efficient execution and smooth multitasking. From switching contexts to communicating, processes are quite the multitaskers, aren't they? All good things come to an end, and so do processes. But how? Well, processes terminate when they've done their job and wrapped up their execution. This could be either after they've naturally completed their tasks, or they could be explicitly terminated by the operating system, or by another process. Think of a process as a guest at a party. When it's time to leave, the host, the operating system in this case, makes sure the guest has everything it came with, and that no mess is left behind. This is the operating system releasing the resources that were allocated to the process. The purpose is to ensure that these resources are freed up and available to be used by other processes. Now, if you remember, every process has a unique identifier, the process ID or PID. When a process terminates, its PID becomes available for reuse. The operating system also informs any relevant parties, such as the parent process, about the termination. In this way, the operating system maintains a clean, efficient, and well-regulated environment. It manages resources effectively, ensuring that no process overstays its welcome or uses more than its fair share of resources. To sum up, processes are the heartbeat of an operating system. They are the fundamental units of execution that make it possible for your computer to do multiple things at once. Whether it's browsing the web while listening to your favorite tunes, or editing a document while downloading a file, all these actions are made possible by the smooth orchestration of processes within the operating system. Processes are created, they execute, communicate, and eventually terminate. Each step in this life cycle is carefully managed by the operating system through a complex interplay of scheduling, resource allocation, and inter-process communication. And there we have it, the life and times of a process in an operating system from creation to termination. Remember, every time you open an application, you're engaging with the intricate ballet of process management.